Okay, welcome to the afternoon session. The first talk is going to be on accelerated Newton iteration for roots of black box polynomials by Anand Lewis and Santosh Vempala. Santosh is going to give the talk.
Thanks. So my co-authors is Anand Lewis, who just started. He's in Bangalore, and he said he's not able to come. I'll tell you something else he said in a minute. He said he doesn't have access to MATLAB. So I spent most of today writing a program, which hopefully will run. Let's see. And my other author couldn't make it also. So here we are. Okay. Here's the problem. There's a polynomial. We assume its roots are real. And we have some upper bound on the largest root, or the magnitude of the roots. And you want to approximate the largest root. Okay. If you have some bound, by scaling, you can assume that it's between 0 and 1 or 0 and a half. So now you want to find this largest root. Here's the problem. So it's monic, so let's assume that the leading coefficient or the highest degree coefficient is 1. And there's some upper bound gamma on its largest root, and you'd like to approximate the largest root to with an epsilon, given epsilon. Okay. A special case of particular interest is finding the top eigenvalue of a real symmetric matrix. In this case, the polynomial is the determinant, univariate polynomial, and you want to find it with an additive error. Of course, there's a lot of independent work just on this problem, where it's not black box, it's explicit. And in this special case, now our goal is to find a fast polynomial time algorithm. By that I mean polynomial in all the input parameters, so log 1 over epsilon and the degree of the polynomial. SVD is usually claimed to be n cubed. I often claim it too. But of course, the dependence on epsilon is 1 over epsilon, not log 1 over epsilon. And that's the most standard implementations and methods. There are many algorithms for SVD. And either they are polynomial in 1 over epsilon and therefore not polytime algorithms, or they're, and these here we're talking about, yeah, or their complexity is at least n cubed. Is that a question? Yeah, so we just want to approximate the magnitude of the largest root. You've got a double-rooted one, yes. But if you add delta to the polynomial, sure. The largest root drops by some substantial amount. Okay. But your polynomial changes its value by only delta. Sure, yeah. So we allow ourselves log 1 over epsilon still. I don't think I understand. I want to find the root with an additive error epsilon. Oh, I see. Right. So, yeah, so I need some lower bound on the root value as well. Is that what you're saying? No, I'm not saying that. Okay. How do you distinguish between having a minimum that's just above zero, a local minimum just above zero versus a local minimum just below zero? It's a real rooted polynomial. Yeah, but you have to actually find the exact root in order to distinguish. Was it a real rooted polynomial? Unless you can actually locate the exact root, you can't tell whether it's above or below zero. Oh, I'm not claiming to tell whether it's above 0 or below 0. I'm only claiming to give you an additive epsilon approximation. But if my function is like x times x minus 1 squared, yeah, or if it's like that plus 0.00001, yeah, then in one case you have a root at 1, in the other case the root is gone. Okay. Wait, this is a real rooted polynomial, right? Yes. So that means that like there is a structural only. Yeah. It is a real rooted polynomial, yeah. We've assumed it. So, yeah, I have actually, I think, more than enough time to give you the complete proof. So we'll see if we. Now, going back to the special case of the top eigenvalue, you can do it by the determinant by saying find, say, by binary search, smallest x so that xi minus a is semi-definite, which you could check by Gaussian elimination. Gaussian elimination on this matrix which has a variable in every entry, which would take n-cube arithmetic operations, but the bit complexity can be exponential if you just do it as is. This, however, can be solved, as shown by Edmonds, using only order n or tilde n bits rather than exponential in n. So this gives n to the 4 total bit complexity, but with log 1 over epsilon. So it is a polynomial time algorithm for the case of finding the top eigenvalue of a real symmetric matrix. Now here is a sort of an older method, the Newton iteration. You have a degree n polynomial. We've assumed all the roots are real, and some upper bound on the largest root. We start there, and here's the iteration, right? You start here, you look at the function value there, you find the tangent there, and that's your next point. So this tangent slope is the function value divided by how much you moved, and that gives you the iteration. You change the current point by the ratio of the function to its derivative. Okay. Now this already gives you a guarantee, as I'll quickly show you. So that's the iteration, and this is a simple lemma I'll prove here. So here's the polynomial. Okay. We assume monic, so I can take it in this form, and it's real rooted. All the lambdas are real. Now the derivative is just this, right, term by term. And therefore, the ratio, the increment, the decrement that will apply in each step is exactly that, which is at most the largest term, xt minus lambda. So you won't jump by more than the gap to the largest root, and you will move by at least 1/n of that. Okay, so each step, you're decreasing the gap. So again, I'm going to assume all roots are within 0 to 1/2 because I have a bound. I'm going to shift it and scale down. Start with, say, x0 equal to 1. The gap decreases by 1 minus 1 over n, at least, and doesn't go to 0. So n log 1 over epsilon iterations suffice. This is a polynomial time algorithm, provided we figure out how to do each step, and that's taking evaluating the function and its derivative. Okay. Now, here's the accelerated Newton iteration, what we present in this paper, which I presume must have been known to Newton. Take this function. Recall the function that we got for the ratio in the increments. We got this function, which is the reciprocal of the sums of the inverse gaps. So now, what we'll do is we'll take this function gkx. So it's the sum of the kth powers of the gaps from the current point to each of the roots. Remember, the current point is higher than the largest root. G0 is n, G1 is the f prime over f. So the standard Newton iteration can be rewritten using this g as xt minus 1/n of this ratio. The n is just to cancel the G0, and G1 by definition was f prime over f. And now here is the accelerated one. We'll use same function, but kth power to k minus first power. And we'll normalize by n to the 1 over k. That's the whole iteration. Before we worry about implementation, let's just see if this is faster and why should it be faster. So here's the iteration. So the claim is, whereas previously, still the gap, how much you decrease will be no more than the current gap. So you won't go below the top root. But you will move by at least 1 over n to the 1 over k. Instead of 1 over n, 1 over n to the 1 over k. So if you use k equal to 2, you get 1 over square root n each time, and so on. And this proof should fit on this slide. So gk of x is this function. That's the kth norm to the power of k. And here is one of the easier norm inequalities. Kth norm to the power of k. Write that summation. Take k minus 1 powers, and one of the powers replaced by x infinity. You get this upper bound. Over here, this is just Holder with k minus 1 over k as the exponent. Okay. So that's just a fact for any vector. Now, same thing, I'm rewriting in this form. Why? Because now we'll apply to x equals that vector, and we get the lemma. Right? That it's at most the gap, the current gap, and at least the current gap divided by 1 over n to the 1 over k. So now you're dropping each time by 1 over n to the 1 over k. How many iterations? N to the 1 over k times log 1 over epsilon. Now this sounds great. You'll set k equals log n. And sounds great. But of course, the question is, you must be paying somewhere in the computation as you go higher. So let's, and we want to figure out bit complex. After all, that was the complaint against SVD or whatever. How to compute this function or the GK value, this function. Okay. So implementing one iteration, here's an observation that you can think of these functions as derivatives. In fact, that's how we first thought of it. G prime k of x, that's just the derivative of the function, is minus k times gk plus 1. And the kth derivative is minus 1 to the k times k factorial, just by explicitly computing the derivatives. So each decrement that we're making, remember each decrement is gk minus 1 divided by gk, is a ratio of derivatives. Now, how should we approximate it? All we have is a function oracle. Right? We can evaluate the polynomial at any given point. Let's say exactly for a second. So first thing you could do is just use a small delta and approximate it and do this recursively, because we need it for the kth, do it for the kth in terms of k minus 1, and so on. If you do it like this, the error grows doubly exponentially in k, which is not totally uninteresting, because then it says that the number of bits you need to keep around are 2 to the k. And so the total bit complexity is 2 to the k times n to the 1 over k. And by choosing k equals square root log n, there's an entire conference for this number, you get O tilde 2 to the square root log n. Okay? Fortunately, this is not the best you can do. We use what's called the finite difference method, which I believe also Newton came up with. At least it was one of the people who came up with it. And the idea is that if you want to do, let's say, the second derivative, you, instead of doing it in terms of the first and expressing it again, you can do it in one shot with just 3 terms. If you were to do this recursively, you're going to get 2 to the k terms. If you do it like this, we want to do it using only k plus 1 terms. That'll be the plan. And the Lth derivative will look like this. So looks like a binomial expansion, but with so the total number of terms is only L plus 1. So in our case, it will be k plus 1. Now the game is, what's the error of this approximation? This is the plan. I have to choose a small enough delta here so that it works, but not too small so that I'm not keeping too many bits around. And so what's the approximation? That again is the iteration. So the plan is the following. First, we'll approximate G1 with G1 tilde using just the first cut approximation. This is f of x. That's the approximation to f prime, right? Alpha will be small, but not too small. And then for higher derivatives, we'll use G1 as the function that we, instead of G. So gk plus 1, we write in terms of G1. Okay? That's the plan. This is exactly the finite difference formula, what's called the forward finite difference formula. And I'm only using forward because I do not want to take the risk of ending up with a point that's below the lambda 1. This is slightly weaker than the central finite difference method, which gives 1 order better error. But for us, when we talk about k, it doesn't make a difference. It's k versus k plus 1. So here's the main lemma. With these settings of parameters, epsilon is the final target additive error you want. Choose epsilon prime smaller than that by a polynomial. Delta smaller than that by a single exponential in k. Only single exponential, so the number of bits is only a k factor higher. And alpha, delta to the power of k, so it's still polynomial in k. Then, if you start with a point that's greater than lambda 1 by at least epsilon prime, it has to be greater by a finite amount now, not just greater, then the first function you're using to approximate is within a small additive factor, smaller than the target, delta to the k plus 1. And then every function that we get here is within a multiplicative factor of a constant. Okay. I'll spend the next 2 slides proving these. The proofs use 2 elementary inequalities that I'll state in a minute. But since we have time. Okay, so that was the main lemma, the conclusions of the main lemma. And these are the 2 facts we're going to use. The first is something about an identity about integers. And the second is for any degree n monic polynomial, real rooted polynomial, you can rewrite it like this, where I'm writing it as a sum of a product in terms of the original function itself. That's the jth derivative, and that's the function. This is again just by expansion. Okay, so the first one you can do by taking derivatives of 1 plus x in a slightly clever way, but that's okay. So these are fact 1 about the coefficients adding up to 0, or exactly -1 to the k times k factorial for up to j equals k. And then the second one is about rewriting the jth derivative of the polynomial itself in terms of the original polynomial. So what's the error? That was the approximation for G1. Right now, this is just the Taylor expansion of f of x plus alpha. And now in the Taylor expansion, the 0th term cancels with the f of x. The first term gives me f prime, which I've pulled out. And then I'm left with 2 to infinity. And then I've replaced the jth derivative by this fact 2, which was the derivative in terms of f. You're taking advantage of the fact that this is a real rooted polynomial. And then now we're approximating these bounds here. This is the x minus lambda 1 will give you the largest one. So I'll put that everywhere. S is of size j, so that's power of j. And the total number of terms here is n choose j. We've just made it n to the j. And then this summation is at most delta prime. Our alpha was chosen so that this happens. It was at least the gap divided by n squared. Okay. Similarly, for the approximation for the higher derivatives, looks very similar. We'll use both facts. This is a definition at the top. All we're doing is writing this function of the sum of the first k terms, but instead of using the G1 tilde that we used, let's assume you do it for the exact G1. We'll do this replacement in a minute. And then this is Taylor expansion. This is, what is this? Oh, reversing the sums, right? The j and the k switched over. Why am I? This is noticing that this summation is the same as k minus I to the j. You can replace by I to the j as long as you put in an extra -1 to the k. And now we'll use the formula, the fact 1, where the coefficients for j less than k disappear. This sums to 0 for j less than k, and sums exactly to -1 to the k times k factorial for j equal to k. That pulls out that gk plus 1 term, and that's the rest. So that was the difference between the two, hk plus 1, which was defined only using the first k terms, and gk plus 1, which is the general function. And this we can bound using here just the, all I've done is added up this sum, put an upper bound for it. And here we're noticing that gj in terms of gk is at most the gap to the power of j minus k. Okay, and that's a summation. That's Stirling's approximation. And therefore, now let's compare directly the approximation with the original function, triangle inequality. First term we just bounded. Second term is based on our approximation of G1, and therefore is also small. That's the error of the finite difference method. So here's the complete algorithm. Set those parameters. Here's the iteration. Now we have to be very careful about one thing. If we get very close, we have to stop. Otherwise, we might cross over. So we're going to check if the increment is small. If it is small, then stop. And if the increment is large, continue. That's it. So the bit complexity comes down to k squared plus k log n over epsilon bits. That's the size of the bits on which you need to evaluate the function. And the total complexity is this. Choosing k equal to log n, the overall complexity is log n times log 1 over epsilon evaluations on numbers of similar size, slightly larger, log n over epsilon. For the top eigenvalue, this gives an algorithm of complexity n to the omega times logs. That's because of Story-Johan's theorem that determinant can be computed with bit complexity O tilde n to the omega. And Frobenius norm of f tells us what an upper bound on the largest eigenvalue. Here are some open problems. Bit complexity of finding all roots, eigenvalues. There is a special an algorithm. I don't know. Weaker assumptions, largest magnitude root of a polynomial. Maybe it has complex root, but I just want the largest magnitude root, and a lower bound on the complexity. This concludes the slides portion of the talk. And here I can run this program, which I labored away. Oops. I'll reconnect. Okay, this doesn't look, let me just run it now. So this is the iteration for a particular polynomial. In fact, it's just 1 plus x to the 1 plus x plus 2 to the n. And the first blue line is the Newton iteration, and then it's for 3, 5, 7. I'll stop here. So you can run it.